So welcome everyone to the afternoon session, and Pawel Caputa will continue with his lectures on aspects of Krylov complexity.
Okay, so hello everyone. I'm going to start with a brief recap from what we talked about yesterday, and then I'll move to more maybe recent or slightly advanced parts, but hopefully I'll try to give you enough material and enough information so you can follow me all the way to the end. But if anything is not clear or you have questions, stop me at any time. So yesterday I told you how to do this expansion of quantum states or the operators in the so-called Krylov basis, Kn or for states, or basis On for the operators that we simply obtained by applying Lanczos algorithm to a Krylov subspace obtained by acting with Hamiltonian on the initial state or Liouvillean on the initial operator. Okay, and the main meat in the story is somehow hidden in these coefficients here, these amplitudes of this expansion, and they satisfy these equations. So these are, I don't know if you can see it from there. There's this Schrödinger equation with Lanczos coefficients ANs and BNs for the states generally. And in these conventions that I use from the literature, there is this Schrödinger equation for the operators that only involves the Lanczos coefficients Bn's. And once we know them, basically we can solve these equations and find the probability distribution Pn of t that captures the entire information about the dynamics of the state or the operator. And the information about these Lanczos coefficients is also encoded in the so-called return amplitude or Lock-Schmidt amplitude, which is the projection of the state at time t on the initial state or operator at time t on the initial operator. Sometimes in the literature there's conventions that you use conjugate of this, but this is, you can easily trace it. And then once we know the moments of these return amplitudes, mu n, there's a nice algorithm to extract generically this an and bn coefficients. So basically, you come to me, you give me this return amplitude, we can compute moments, extract coefficients, plug them to this equation, solve them, and extract again this probability distribution. And once we know this, then we define the so-called K complexity or spread complexity or Krylov complexity. It's still a very young area, so to say, so there are still many names around. That is simply defined as an average position on this one-dimensional chain that I explained yesterday with this probability Pn. Sometimes I didn't talk about this yesterday, but this may appear today. Sometimes it is useful to think about this complexity as an expectation value of a certain operator that is dependent on this initial state in Hamiltonian or the Krylov basis, which is basically this K operator that is sum over all the K basis vectors with the coefficients n. Okay, so if you simply plug it, it is true that the expectation value is exactly this K complexity. And of course, this algorithm or this story is very general. You can do it as we discussed yesterday. You can plug it, test it for eigenstates, for some simple examples and so on. But of course, we are interested in this. At least I try to be motivated by these holographic applications of growth of operators or growth of the thermofield double states. But again, this is very general, and the only thing that will change depending on your question will be this return amplitude. So often in the literature, at least at the early stages also, people were concerned with this return amplitude given by thermal two-point function. This is given this Weidmann inner product that I described yesterday, which is basically thermal two-point function with one operator regulated by this beta over 2 along the Euclidean time. So these objects also appeared yesterday on Ragu's talk. And for example, another case that I will also discuss will be the return amplitude for the time-evolved thermofield double state. You can evolve it either with left Hamiltonian or just left plus right. And in that case, the return amplitude becomes the ratio of partition functions of your system, with beta analytically continued to beta minus IT in the numerator normalized such that at t equal to 0, these return amplitudes are always to 1. Okay, so again, depending on your questions, your return amplitude may be universal or very model dependent and very complicated, and you might get very universal or very model dependent questions. But basically the thing is to find based on this return amplitude to find these Lanczos coefficients ANs and BNs and try to solve these equations. That's somehow the rule of the game. Before I will go, this will also, I'll mention this in the holographic application. There's a so-called continuum limit that is often very useful to get some qualitative information about the system or the growth of this complexity and so on. And we can basically define this continuum limit based on the Schrödinger evolution equations by introducing the continuum variable x, which will be some small epsilon times n that we keep fixed. And then we can promote this amplitude phi n of t to simply a function of x and t. And then the Lanczos coefficients, I'm describing it here kind of historically based on this second equation for the operators. Then we describe this position-dependent velocity as simply Lanczos coefficients Bn times this epsilon. And if you simply plug this new variables, this substitution to the second equation, and you expand to the first order, you get simply this equation, this differential equation here. So you get time derivative of this function plus the velocity x plus derivative of the velocity times the function. And this equation, if you know the initial profile, of course, we always know we more or less know the initial profile of this wave function. We choose the boundary condition such that this we are localized at n equals to 0, at t equals to 0. But also, if you can, this equation is an integrable equation in a sense that you can easily solve it in many cases if you know the velocities. So this is how, at the beginning, people were tested what are the possible behaviors of, like qualitative behaviors of these Lanczos coefficients and how does the complexity grows if by solving simply this equation. Here I wrote this equation in a kind of nicer way. So this is something you're familiar from your quantum mechanics. You can always write the Schrödinger equation as some continuity equation. So you can basically take the same equation and rewrite it for the amplitude phi bar. If you multiply this one by phi bar and this one by phi and add them, you can rewrite this equation as simply an equation for the probability, P of x of t. And this equation becomes a continuity equation for the probability. So the time derivative of this probability profile is the x derivative of some current that is velocity times this probability. Okay, so this is equivalent, and then you can easily solve it for various things. And often in the literature, you might also find people discussing this continuum limit of this spread complexity or Krylov complexity is simply 1 over epsilon squared, the integral of this probability times the x dx as a continuum generalization. Okay? Are there any questions? Yes, please. So generically, if the operators are non-Hermitian, there could be ANs also for the operator. So this would be the generic equation. But often we choose ON to be some observable. And that means, like, because of that, in the return amplitude, we often get a symmetry of sending t to minus t. And you can show that in all that cases, ANs can be set to 0. Once you simply have this symmetry, once you start with the return amplitude like this, you expand it, you will see that you only get even moments. And when you only get this even moments, once you solve this Dyke path counting, you will see that ANs are simply 0 in those cases. But generically, you might be interested in non-Hermitian operators perfectly. The growth of those operators, and then this is the most general equation, at least in this simple setup. Thank you. It has in some sense, yes. So there will be, of course, some initial profile, px of t, that you can choose. So it can be Gaussian or whatever. There will be some information about the initial conditions, but also velocity indeed. Like velocity is the continuum counterpart of bn's. So these bn's, they will both depend on the Hamiltonian and on the initial state. Right? So they are related to the moments, which are various powers of the Hamiltonian in the initial state. Yes, you can also generalize these equations with AN. You can just take continuum limit of ANs and so on. Okay, great. So let me just now quickly go through some class of general results. This has been going on for several years, and there's a zoo of papers coming quite often about various new models where this is being computed, and there's some new interesting behavior of BNs and ANs in this model, and so on. So I will not, of course, have time to discuss all of this exotic or nice and interesting behaviors depending on integrable or chaotic, but I'll just describe some general thing that will be useful in the holographic applications. So actually it started from the papers. Sorry, I'm also being quite bad with references for various results. So I hope you can find this in a nice review by Pratik and collaborators where they put all the references and so on. So if you want to check where things were computed. But so I'm just gonna quickly skim through these computations. So actually this was first found in this paper by Parrikar and collaborators, and they noticed that these BNs, they can at most grow as linearly in this n for large n. And if this is the case, then this Krylov complexity for the operators grows exponentially as exponent of 2 lambda times t, okay? And then in this way, you can define a Lyapunov exponent from the Krylov from the operator growth, simply this 2 alpha, and in the SYK model that they considered, it happened to be coinciding with the OTOC Lyapunov 2 pi over beta. Okay, this is one example. There has been various studies of this continuum equation, and also people confirmed this case where, for example, this velocity is linear in x. By some normalization, you can indeed confirm that this complexity grows exponentially with time. There are some sublinear growth cases, for example, where this velocity grows as x to some power delta with some coefficient lambda, then generally this complexity can grow as t to some power 1 minus delta. And this can also be checked on before going to continuum on the lattice, that whenever we have the growth of Bn that goes as square root of n with some lambda, then complexity usually grows as t square times this the same coefficient alpha square for late times. Actually, this is the case, for example, in JT gravity for early times, and in many cases as well. And finally, for very late times. Actually, I have not written the time periods for which we usually find this growth, but basically we often find that. Sorry, this is should be constant here. Usually for very late times, we find in generic finite dimensional spaces that these velocities or Lanczos coefficients go to constant, and when this is the case, actually we observe a linear growth of complexity. This is the period of linear regime of the growth of complexity where these BNs are constant. So in other words, whenever you for example, I give you some return amplitude, you look at the different behavior of Lanczos coefficients as you change the n, and if you can fit this behavior of Lanczos coefficients into these regimes, you can either solve this equation and you can compare that this will be the case. And what changes, of course, will be this different Lyapunov or different constant and so on, but qualitatively people have already studied it. So you don't need to again solve these equations explicitly, but you can, if you want to have some qualitative information, but you can try to see whether your Lanczos coefficients match any of this behavior. Okay? And
you said a little bit more about the times there.
Okay.
Somewhat related.
Yes.
Here is that somewhat related behaviors.
That's right.
Studies in our random matrix model.
Exactly. So I will talk. Okay. Thank you. So I will indeed. So in the random, let me just be a bit more precise. So these cases usually in the basically also I was going to say first maybe think in general in random matrix models or in finite dimensional systems, what we see is like that this Bn coefficients they initially grow. They might actually have a period of a linear growth up to some constant that we normalize. This is drawn as n, small n over capital N, where n is the size of the matrix. And then once they reach the maximal value, they actually go to a constant, as I was drawing here. And that means that as a function of n, at the end, as a function of n over n, this constant means that they finally go to 0. Okay, so this is a canonical, this is a kind of generic behavior of these BNs. And this behavior of BNs correspond to this growth of complexity. There's some initial quadratic growth, goes through the linear, and then it saturates to some finite value. Okay, And now is the question of timescales. So usually also in these random matrices, this growth that we have here, usually we observe it for times of order t between 0 to log n, where n is the size of the matrix, for example. This times here is the period, this time period is much larger than am I getting these times right? Yeah, this is usually for the very late times. So this is for times much bigger than log n. So basically, this is like an early, and this is a late time regime. I think this is right. And this can happen either right after this one, or depending if the model is chaotic or integrable. Okay. Yeah, I think so. I think so. I'm hesitating generally. Yeah, I think you can define it as a scrambling time. Yeah. Okay. Sorry. It's a good question. So actually, you cannot see it from simply from this equation. There's some. I think there's some modification. You would probably have to take. I will talk about the saturation in a moment. And people have tried to understand this saturation from taking the continuum limit, and you need to take like a second derivative of this equation to capture for the phenomenon of something that I will discuss in a moment. Okay. But here, somehow here, this kind of diffusing equation, some of the point of this equation is always you can rewrite, you can introduce some variable y such that you can rewrite this equation dy times phi of y of t. So basically, this is like some right or left moving wave, and that's why this always, you can capture the growth of, but not somehow the return. And this will be important for the saturation. Please. Is the time at which the saturation starts is log n? No, not necessarily. Not necessary. I'm just saying that for times bigger than log n, you have the period of the linear growth. At least in the studies of random matrix in numerics. I will tell you more exact times now for the thermophile double. So yes. Sorry. Yes. I think this should be Bn over n.
Yeah, because Bn's are basically depend on eigenvalues.
Good. Yeah, of course. So this is in this plot. I think they are rescaled, such that the maximal one is real zero now.
What's the maximal and minimal eigenvalues corresponding to this system Hamiltonian that you compute Bn maximum? What's the upper lower bound eigenvalue?
If I understand your question, if you have the maximal Bn. Yes.
Because the eigenvalues are basically some combination of the Bn combination of eigenvalues.
Yes.
The eigenvalues are also bounded by some, right, in the scale that you scaling these.
Yes.
So what's the scaling of the eigenvalues?
Well, this is for random matrices, right?
Yeah, so that's why I expect some universal scaling of the eigenvalues.
I don't know in this case. Do you know what is the? No, I think this is some generic behavior in random matrices. I'm not sure. Like, I think people in the continuum, I think Javier and Vijay, they studied like what's the relation between density of eigenvalues and the distribution of Bn's. But I don't know what's exactly the relation between the maximal and minimal in this random matrix. Thanks. I'll try to look it up. Okay. And but there is a nice, so this was mostly for operators. I was describing mostly B's. And now we can do it really for the random matrix. So let's do, again, random matrix theory. I choose some Hamiltonian to be n by n matrix that belongs to GUE, example. And let's consider this question of evolving a thermofield double. In that model, okay? So I told you that for that, we basically need to know S of t, beta minus IT over Z of beta, and we need to find moments, and from these moments, we can extract ANs and BNs and compute basically the spread complexity. What is interesting is also that, of course, this thing we usually know numerically, and what we can do is that there is very nice packages to put any n by n matrix into a tridiagonal form. This is called the Hessenberg decomposition of a matrix. So once we have this matrix in the Hessenberg decomposition, modulo some minus signs that we have to take for BNs, because usually Mathematica gives you some minus signs of diagonal. They're related to, in our case, these BNs are basically normalizations of these vectors as I was defining it. You can extract numerically all these ANs and BNs for any large number n, and you basically get the Lanczos coefficients for free by this Hessenberg decomposition. And there's also one issue of an initial state. So basically in Mathematica or in Python, if you do Hessenberg decomposition, Mathematica does it for the vector 1, 0, 0, 0. So first you need to sometimes rotate whatever you mean by your initial state to that Z1, 0, 0, 0, and then you exponentiate your numerical matrix, and you have basically all the wave functions computed for free, at least numerically for any times, and you can study how this works in practice. If this has also been done by Vijay and Javier and guys, you can also study some generic initial state and then look at the evolution using this Hessenberg decomposition. And these are what I'm going to show you now. These are the results. So basically, BNs grow very much like those ones there when we rescale them. At the initial times, we also have AN coefficients for the thermofield double state, but these AN coefficients very quickly grow to 0. So basically, for later times than the initial growth, then you only have BN coefficients that govern the dynamics. And in that cases, now let me draw how the complexity looks like. So I'm drawing the complexity over n, and this is T over n. And what we observe is that initially, and generically, this complexity grows quadratically and goes into a period of a linear growth and then saturates. Okay, let me maybe first draw it. So basically, this is the generic growth as a function of when we increase beta, it can go like this and slightly smaller. So let's say this is for beta equals to 0, and this is beta larger than 0. But we have basically 4 regions, which is the, we call this region a ramp. This region is peak. This region of falling is slope. And finally, you get a plateau. And here we can really check what the timescales are. So basically, the timescale is of order 1, but you have to notice that we are drawing here t divided by n and c divided by n. So basically, this is like roughly log of the number of degrees of freedom. So should I write it as a log of the entropy? Yeah, I think log n. But then finally, this saturation time, where this peak, where this thing is saturated, it's actually very late. So this saturation happens as exponent of the log of the entropy. So let's say this is of order entropy, or well, this is scrambling time, and this will be exponentially in the entropy, I think. So the capital N will be just the n size of the matrix. Log of, yeah, I was sure that I was going to mess up something with this log. Basically, this peak, okay, now let me explain to you how do you understand it from the, I think we used, one second. Yes, yes, yes. So I'm taking n by n very large number, say 1,000 by 1,000 random GUE Hamiltonian, and I'm computing, I'm finding eigenvalues, I'm computing the thermofield double, and I'm doing the evolution with the same Hamiltonian. Okay, and this is the plot for the spread complexity for that state. I'm just getting slightly confused, as always, with this precise time scales. I think it should be that you reach the peak in the exponent of the number of degrees of freedom, and then you such that the very late times is exponent of the. It's a very late times, like doubly exponential. And of course, here we cannot see the. Of course, at the end, you also expect some. You know, Poincare recurrences and so on, but this we cannot see on this numerical analysis. But okay, now there's a very nice picture for this from this one-dimensional chain. So as I was describing to you, at t equal to 0, here I'm going to be plotting this probability distribution P of t. So this is P of 0. I told you we are basically peaked at n equals to 0. Okay, this is time. And then as time progresses, we notice that basically this probability distribution that tells you like where on this one-dimensional chain you are supported moves to the right ballistically. So you have some small tail here, and then it basically proceeds for times larger than 0. But then the Hilbert space is very large, okay? We take n very large, but then finally you reach a time where ES, where you, on this one-dimensional chain, you reach the most complicated vector in the Krylov basis, which is basically bounded by the dimension of the Hilbert space. So basically this time, so basically this is the period of the initial growth and going up to the peak. This is the ramp. But once we have this is the peak time. Is exactly when on this one-dimensional chain, okay, there's still some small fluctuations here, but you reach that most complicated vector. So it's roughly n. Well, I mean, it's random matrix theory, so you would naively think that all of them, it's some change of basis in the random matrix, so maybe all of them satisfy TH. Yeah. And then no, they are no. So these are the Krylov basis vectors. Okay. So I take eigenvectors, of course, and then I change the basis into a Krylov basis by this Lanczos algorithm. And this is what I'm saying. Like this is the time where you reach the most complicated vector in this Krylov basis. Okay. So this is the end of the chain. And that's exactly the peak time. And after that. If the width? If the yeah. No, why should it grow with n? Yeah, so it's like a particle. Well, it's like a particle on the chain that just hops to the right. Okay, but of course here I'm plotting this. I'm plotting it numerically. We choose some initial profile, and then we can compute these wave functions numerically and evaluate this probability distribution numerically. And once we plot it for different pictures at different time windows, we see that basically it looks like some kind of wave, well, like some kind of thing just moving on this one-dimensional chain. So this is just, sorry, I'm just being really, so this is n, okay? So I'm going from n to some more complicated on this one-dimensional chain. And then after some particular time, of course, the state, I'm going to reach the finiteness of the Hilbert space tells me that there is only a finite number of vectors that I need to span this evolution, and that's precisely the peak time.
Sir, hello.
Right. Well, no. So indeed, that's the case when you, for example, when you study the operator evolutions, you can solve some of the wave functions, and you plot it. Initially, the wave function is peaked at the origin, but then somehow it moves. For late times, it becomes basically spread over the higher ends. Well, basically, the truth is that the higher ends, phi ends of t, they become, they kind of go more to the right. But if this is the result for random matrices, so if we just plot what am I plotting? I think. The scale. Sorry, what I'm plotting is like the probability distribution, so all the PNs, okay? So at the bottom we have n's, and from 0 to some particular value, and I'm plotting I'm evaluating at particular time window t equals to, I don't know, 10. I'm plotting all the probabilities. Okay, so you can see that basically all the probabilities at this particular time, the Pn that is here, it just goes to the right. Yes. It will be growing with time. Well, I think the good way to characterize it, you can just look at the variance. So you see, like, this is the average position, right? Like, for example, this case, and then you see that for very late times, the variance is actually, it saturates, it doesn't grow. So it means, like, you're, yeah, it's the wave functions are like, there is some spread that we can. I don't think we really looked at the spread numerically carefully, but they are pretty much peaked at Pn, and this Pn, that it's getting dominant is correlated with time. So as n goes, that's why we see basically this peak from this different probability distribution. So yeah, I'm not sure if I explained this clearly enough, but. Maybe we can discuss this a bit. Like, this should be something very simple in the sense that it's just plotting different probabilities for different times, and from that you can also read off this plot pretty much. Okay. And then what I wanted to say is that after this time, what you get is that basically after you reach the most complicated guy, this guy starts to so the probabilities, the distribution of probabilities starts to turn back. So you see that it kind of goes down a little bit for different times and so on. And this is the period of the slope. And then for very late times, basically this is like kind of randomly distributed on the whole one-dimensional chain, and this is exactly the plateau. Okay, and sometimes the value of this plateau can be estimated. So it depends on the temperature, but roughly goes like n-1/2 if beta is equal to 0. No, well, okay, so the. Well, okay, so what? No, so it's well, if you plot, okay, depends how we define the variance, but we define it as just the absolute value square, like the average position normalized by the, and that goes to a constant. That also saturates. So it's. No, so what I mean here is that it's basically there's no more evolution, in a sense that this probability is just like some constant noise on this one-dimensional chain. So there's no movement. If you want to think about it as this position particle on this one-dimensional chain is basically this peak describes this position, but for late times this particle is roughly not moving. It's just some very small noise.
Sir, am I audible?
Sorry, sir, yes? Yes. No. So this the peak is where you reach the most. So here there's a growth. Here you reach the most complicated vector. here this peak means like from this going up, it starts like being distributed everywhere on this one-dimensional chain. And then for this one-dimensional, for the chain, when you have very late times, that basically the probability is constant. Okay. Yes. No, so the vectors don't care about this, right? Like the Krylov basis vectors are, you just compute them once and for all the evolution by this Lanczos algorithm. But what is important is this probability amplitudes, phi n's of t's. Okay, and then depending on different values of bn's, this probability amplitude will have different solutions, of course, from the Schrödinger equation, and it's basically the same mechanism as we have here. Okay, so these bn's, they become constant. They are constant, and they go this for very large n. This goes to 0. Okay, and that's why even in random matrix we also see the saturation. So it's the same. It's the same mechanism for the. You basically solve the equation with these bn's. What is a bit non-trivial is actually this form from going from peak to the slope. So this we can actually nail down to be sensitive to a correlation between eigenvalues of random matrices. So we have repeated the same exercise by simply taking an n by n matrix, but drawn with eigenvalues drawn at random from Gaussian semicircles. So you know that by construction, this gets rid of the correlations between the eigenvalues. And for example, for this spectral form factor, this gets rid of a dip and the ramp. And here we actually see something similar. So if we do this if we just draw this eigenvalue, so if we construct the Hamiltonian by drawing eigenvalues in random, we see this period of the growth the same roughly, but then we have a saturation to a plateau. So we will not get a peak and the slope. Okay, and this was our numerical observations in all these random matrices. And by now people understood, and actually even today, or there has been a lot of papers lately trying to really show that this peak and the slope are really some smoking gun of a chaotic versus non-chaotic behavior of a system for evolution of the states. So sometimes, you know, this initial quadratic growth is universal, and linear growth, depending on time scale, but is also universal. So it can be shown that it exists also in some integrable models. But actually, if we really tweak the model such that if we break the integrability, we can show that this peak and the slope disappear, at least in some examples. I don't know if there's already a proof, but there's some good indications about that.
So Pawel, just one question. So in case of integrable systems, do the peak appear or are they not there for the integrable systems?
So what will disappear?
Just for the integrable systems, what kind of behavior will this show? Like the peak ramp plateau will it be there or?
Yes. So peak and slope. I think when people studied it, for example, in SYK, there's some integrable version of SYK versus non-integrable. So people notice that this peak is not there. Or okay. I don't know if we know in general systems what will happen, if there's any proof. But definitely, if you go between integrable and non-integrable SYK, you see that peak and slope disappear, and you only get the growth and the saturation.
Okay. Thank you.
Sir, am I audible? I have just 2 questions I wanted to ask.
I don't know.
Hello?
There should be, you mean the value of the peak or for how long it lasts and so on. Yeah, if this relation between chaotic and non-chaotic is true, there should be. But we only have like a bunch of numerical data for the moment, and I don't think people study that yet. That's a good question. Yeah. I think that's right. So I knew I was going to mess it up. So this is really order 1. which means like if you really look at the times, this will be the exponent of the, yes, so this will be of time n, which will be log of the entropy, right? Exactly. So log of, well, this, yeah. You're right. I think this should be like, if you look at the paper, they will be correctly assigned there. I'm really sorry. But it should be order 1 if we divide by n. Thank you.
Can you say something about interpretation operators size? Like what does it mean after the peak that it declines again? Because like usually growing complexity it makes sense. Like if the spread gets bigger and bigger, so what does it mean that like declines at some point?
Well, I mean, so of course this is for states, first of all, but I mean the way we understand it is that okay, you have some phase space or space of states that you're starting from some initial point on this phase. By some generic evolution, you are allowed to explore. Okay, and then of course the growth is that it's easy to explain. You basically once you do the evolution, the states you can think about it as a particle moving in this phase space explores more and more of this phase space. And then at very late times, you go into some corner of the phase space you explored so much that there's nothing more to explore. So you basically visited all the states. And then you start wingling around and so on. So this is, well, these are basically not my words, but how Lenny usually draw his pictures, that complexity should grow, and then for very late times it should saturate, and then it should go down and so on. So I believe this is the same mechanism here. It comes from the finiteness of the dimension of Hilbert space.
Different in time than let's say very late times.
No, these are like I think I should have drawn this like carefully. These are really very late times. So I think exponent of the entropy. Yes. Oh, the slope you mean by why? Okay, so the slope is like okay, you really go to the end and then, but you still do the evolution. Okay, you still move like the state keeps evolving. Okay, maybe you compute 1-point functions. I don't know, entanglement entropy, whatnot, and they are already saturated long ago, but still like e to the minus iht of the state is still moving the initial state somewhere around the phase space. Okay. To be honest, we don't fully understand why like hitting the most difficult vector and then going to the left, going back should be it's definitely some interesting characteristic of this spread complexity. And if what people claim is true, that is really sensitive to chaotic versus non-chaotic, then there should be some nice mechanism to explain it. But I think this is mostly empirical or phenomenological for the moment. Yes. Yes. Well, well, yeah, like it's also related to Finn's questions, like somehow what's the relation between the final plateau and the peak, and how can we really quantify it in terms of some physical I don't think anyone has done this carefully.
But this is a kind of dynamical slope because it happens. So how good it is to slope something integral non-integral by a dynamic slope because it could be.
Well, it's a dynamic probe, but it's based on the partition function, right? So I think we also know that the spectral form factor, which is based on this partition function or square of this one, is also a good definition, right? So I mean, I don't have a sharp answer to your question, but I agree. It's a dynamics, but somehow the dynamics has the same information that the spectrum, right, and the partition function. So
if you compare the spectral factor, there is
yes, yes. I mean, what we can really compare this to the spectral form factor, and we see that it has deep and the ramp and plateau. And when we remove the eigenvalues, and it also when peak and slope disappear, the deep and the ramp disappear in this spectral form factor. Well, in a random matrix, it was linear. Yes. I mean, in some simple examples, we can actually see that this complexity looks very much like 1 minus the spectral form factor if we normalize it appropriately. So there is like obvious that they are correlated, but in random matrices, I don't know. Okay. Sorry. So maybe thank you for question. So here I was drawing like the generic behavior for random matrices for operators, right? So this here we only have these BNs, and then they keep growing, and then they saturate. Somehow for operators we don't see this peak and the slope. We only see the growth and the plateau for random matrices. Whereas this is the picture for the states. So we did it for the thermofield double, but then also people did it for some random states picked up from your random Hilbert space, and then doing the evolution with the random Hamiltonian. Yes, and saturating. Yes. Exactly. That means that something more is happening. I mean, this is probably related to some extra correlations, like between these eigenvalues and so on. That's why when we're removing them, we're getting the same thing as the operator for the state. Thank you. Yes. If it always had a spread.
Like over here, if it's very sharp, then later on somehow the dynamics knows that this Hilbert space is fine. Yes. It has somehow to close on itself, and then it has to spread. So in that case, mathematically you can see that the expected value will go down. But if it was already spread, then I would imagine that it may continue.
I see. Okay, maybe we can discuss this. So I need to think about this. Sorry, but actually my time disappeared. So okay, perfect. So I'm just kind of lost here. Very good. And let me just show you one more example before I really go to this hologram. Is there a better one? So this is actually quite useful, and maybe a kind of cheat trick that if you're going to work on this, I encourage you to check it. Namely, I was telling you that basically this Krylov basis works in such a way that basically these ANs appear as a diagonal piece of this Hamiltonian in the Krylov basis, plus we get Bns times Kn minus 1 plus Bn plus 1, Kn plus 1. And basically you may take an ansatz that in this basis, so this is really your physical Hamiltonian. Sometimes we write it like with some star that is really the representation that depends on the basis. You can write this Hamiltonian as basically some gamma coefficient times something diagonal plus some alpha coefficient times some rising operator plus some lowering operator, okay? Such that basically this gamma times L0 acting on Kn will be your An, and alpha times the lowering guy on Kn will be Bn times Kn minus 1. And similarly, alpha times the rising will be Bn plus 1, Kn plus 1. Okay? So this doesn't buy you anything. So this is just some funny rewriting. But Actually, when there are cases when it actually buys you something, namely where this L0 when this L0, L1, and L minus, this L0 and L up and L down close some algebra. Okay, so this is some phenomenon that is quite well known from integrable systems or quantum dynamics, where basically system has Hamiltonian has some particular properties, but then when you study some dynamics of evolution of particular state, there's some emergent dynamical symmetry behind that evolution. Okay, so let me show you how that how this works for a particular case where L0 and L1 and L minus 1 are the rising and lowering operators of the SL2R. So basically, they satisfy Ln, Lm, n minus m, Ln plus m. So basically, we assume that the Hamiltonian in this Krylov basis can be written like this, and then the Krylov basis vectors can be written as some normalization n factorial gamma 2h gamma 2h plus n L minus 1n on some highest weight state h, where h is an eigenstate of L0. Sorry, it's killed is an eigenstate of L0, and it's killed by L1. Okay, so this is your standard representation theory of SL2R. And if this is the case, you can actually see that basically these KNs, this is the natural basis of your SL2R Lie algebra, but it's actually also a Krylov basis of a Hamiltonian that is written in terms of L1, L minus 1, and L0 generators. So for example, if you write this Hamiltonian in this Krylov basis again, you will see that it will have all these ANs on the diagonal and BNs here and 0 everywhere. But actually, these ANs and BNs, they will be automatically fixed by the algebra itself. Okay, so for example, let's check this one. So you see that this L0 acting on this Krylov basis vectors. So basically, Kn, we can write it as basically a vector h and n, which is like a n ladder operators acting on this highest weight state, and we know that gamma times L0 acting on Kn will simply be gamma n plus h plus n on Kn. So we immediately read off what the ANs will be, and we can do the same by the representation when we act with L1 on Kn, so on this vector h and n times alpha. You can see that this will be alpha times the square root of n plus 2h minus 1 on Kn minus 1. This is just standard representation of SL2R, and you can see that this will be the Bn fixed by this SL2R algebra. And why am I saying this? You see that here you get three numbers. You get this gamma, you get this alpha, and you get h. Okay, so this dynamical symmetry completely fixes this Krylov basis and the Hamiltonian evolution up to these three numbers. Okay, and then if I come to you and give you some return amplitude, and you compute moments and ANs and BNs, and you realize, oh, these ANs and BNs actually they have this form with some particular alpha and gamma, then you are in business. You can immediately, you don't need to solve this equation. This Lie algebra will solve it for you. You basically use powers of coherent states to find the wave functions, and the whole problem is done. For example, for SYK, you get this alpha to be pi over beta if you want to study operator growth for the SYK, and gamma equals to 0, and h equals some dimension of the SYK operator. But this is much more general. It's really some dynamical symmetry. In general, it has nothing to do, well, almost nothing to do with the underlying SL2R symmetry of your of your system. It's really a dynamical symmetry on this one-dimensional chain. Okay, and this will be very nice and important. And yes. Yeah. So okay, very good. So I'm going to discuss this now quickly. So the point is that whenever you have this dynamical SL2R symmetry, you can this can happen for your initial state. Does not need to be this highest weight state. Actually, it can be some coherent state of some of this SL2R algebra. So you can displace it and so on and so forth. But whenever this SL2R applies, you can find that this spread or Krylov complexity has this nice form. Okay, where this D parameter or alpha square minus gamma square. So this is these are these alpha and gamma parameters of the Hamiltonian. And B1 square, let me remind you, this was the variance. So it was mu1 square minus mu2 modulo my I convention. So but I think it should be, so this is the information about the initial state, whatever that is. Okay, so this is the square of this B1 is the variance. Okay, and let me comment. So I don't know. Just let me repeat this this whole story. Basically, whenever you have, of course, you have to do the calculation first to check whether your return amplitude gives you that SL2R dynamics on the 1D chain. A priori, I would not be able to say that this was going to happen. But when it happens, and it happens in many nice examples, then basically the spread complex, the Krylov complexity has this. You can factor it into these two parts. There's one part which is this one, and it is only dependent on the data of the Hamiltonian. Okay, so it's fully this time dependent part is not dependent on the initial state at all. It only depends on how you tweak your Hamiltonian with this alpha and gamma parameters over there. And the only initial information about the initial state comes through B1. Okay, and it comes through the variance. And this is quite nice. So people have observed some instances of this formula in various cases. So for example, one universal instance of this is that at the initial time, the complexity grows as B1 squared T squared. Okay, this actually holds empirically in systems where this SL2R symmetry is not present. So this initial universal growth of B1 square has been observed elsewhere. But actually also from this formula, you can find at late times that you can define the so-called scrambling time from this Krylov. And you see that this goes basically as this D star, where D plays the role of the Lyapunov exponent for these systems. And T star is simply given by 2 times D log of D over B1. So you see that the information about the initial state only enters this scrambling time. Okay, it's become, after this time T, it becomes scrambled, and the evolution of the system forgot already about the initial state, and it only evolves with this Lyapunov L. And also, I should have said that there, for whenever you have this SL2R, it's an infinite algebra. So n goes from 0 to infinity. It's not bounded. But you can do it for finite cases where you have SU2 algebras or some other the algebras there. The range of n's there is usually finite. But here it's infinite. Okay, so this SL2R describes this initial growth and then this exponential growth forever with this universal Lyapunov. Okay, perfect. So thank you. So also from this regime, we have three cases. So we have basically case when gamma is less than 2 alpha. And in this case, we have an exponential growth of complexity with this dt. We have the case where sometimes in the literature, in a very similar analysis for the evolution with such SL2R Hamiltonians, this comes under the name of inhomogeneous CFTs, or sometimes appears in Floquet drives and so on. People refer to this regime as thermalizing. There is a regime where gamma is bigger than 2 alpha. That's actually oscillating. So this is non-thermalizing. And then gamma is exactly on the threshold equals to alpha. Then this is basically complexity grows quadratically. Okay? So this is as much as you can already read off from these different behaviors of the dynamical SL2R. Okay. I will use this. This will be useful now in some holographic applications, but it's actually a very useful. It's a very useful tool to basically not only for this SL2R, but for other algebras if you want to solve these equations without really solving them, or if you want to know what are the qualitative behaviors of these coefficients and how to classify them and so on and so forth. There's some nice story about bounds on the growth of complexity that actually this also plays a role, but I will not have time to talk about. So, okay, good. So here where the model enters, this is very universal if you have SL2R symmetry on the 1D chain. But where model enters is this alpha gamma and the B1. Okay, so this is the information about the model. But not every model can be put into this form, unfortunately. Okay. So I think that's as much as I had to say about these technicalities and what is known and what is not known about this Krylov and spread complexities in the kind of say boundary side of the story. Again, there is a lot of topics I have not had time to cover, like for example, open quantum systems. There has been also some nice progress on that. Even yesterday, there was a question about time dependence. There was a paper yesterday about time-dependent Krylov bases as well. So it's a very active topic, and many things are evolving quickly, but mostly on the boundary side. So now in the remaining 20-something minutes, I want to focus on some holographic parts. That's right. Why is it exponential? Because here the Hilbert space is exponential. Sorry, it's infinite dimensional. So you basically this initial growth it can grow forever. Okay. In SYK model, actually, we have the exponential growth if you use the large Q correlator for the return amplitude. At finite, and I think not. No, it's saturating, right? Yes. Yeah. With random, but large Q analysis.
I should ask earlier, but for the random matrix model, you said that the propagation of Krylov wave function is kind of ballistic.
Yes.
And is this a specific feature to this fast scrambling system, or more generally true? In which case, this Krylov wave function has this ballistic propagation?
Well, I don't know if this has to be fast scrambling, because you could solve the ballistic spreading also from this continuum limit, from this probability, right? Yeah, I think your question is related to the kind of confusion also in the literature, or questions whether scrambling is the same as chaos, as quantum chaos, and so on. So I think at least in this setup, it's just the usual kind of ballistic spread of the operators at the initial time. I don't think this has to be related to chaotic properties necessarily. But I think chaotic models will have that. Or yeah, maybe as a part of the definition.
Hi, Pavel. Just like I would want to know your comment on today's paper on archive, like because since you talked about chaos, right? So today's paper said that the way it saturates reveals the chaotic properties of the system. So what do you think about that?
Can I like not to answer this question?
Okay, fine.
I'm sorry, I have not read the paper carefully enough. So
Okay, fine.
thank you. Okay, good. So let me go finally to some really, I think, exciting part that is probably new and some things I motivated my lectures with. So in the first lecture, I was explaining that, okay, whenever there has been all these nice discussions about what complexity will do for us and how nice tool it will be and so on and so forth. But somehow, like for a long, we did not have a concrete, or there were some definitions of complexity that were not. There are still some definitions of complexity that are not immediately applicable to questions that we were asking in holography. So in my up to now, I try to describe to you one proposal for complexity that is kind of now accepted as a tool in many body system, and we try to see how it performs against our hopes and intuition for this holographic complexity models. And so the first thing I wanted to mention, I don't know if I have time to mention the second one, but at least the first one was the relation between the complexity and the momentum. So basically, as I was telling you, we have some picture that there's some particle with some mass m that falls into a bulk of ADS, maybe there's some black hole. And this particle has some radial momentum r as a function of t. And the claim was that if we have some complexity measure that describes some growth of the operators or spread of the operators in some particular way, then it's the rate, so basically the size of this operator, or maybe the complexity of the operator, should be related to this radial momentum, the function of t. And the proposal was actually, it was tested in some simple examples that they should scale at late times more or less the same way. But after a series of papers by Lenny, and also actually nice works by Ying Zhao, together with Saskind and other people, they kind of made it a little bit more precise that if we find at some point some measure of size or complexity and we compute its rate, then this rate should be roughly related to some absolute value of this momentum of this particle falling into the bulk, okay? And they had various epidemic. There was, of course, by the time, there was not really a definition of complexity or kind of precise way of computing this quantity in the boundary, but they were using some nice epidemic models or some effective counting of gates to argue for this relation, okay? So now I described this spread or Krylov complexity, and I'll try to see whether such a relation can be tested and whether we can fix, if it's true, then whether we can test this coefficient here. Okay? Sorry, thank you. So initially it was argued that somehow the complexity should be related to the momentum, like how they grow. This was based on some large late time scaling of this one, but in a series of papers, they finally proposed that the bulk momentum of this particle should be related to the rate in which complexity grows. I don't know, this was argued, but has not been tested. So, I mean, I'm a very simple-minded person and I need to, and this is, okay, so this has been tested a little bit in, presumably, yes. So I'm a very simple-minded person, and I really wanted to do a calculation of something like that in two-dimensional conformal field theories. In SYK, there were some results for the size computed in one, so one could argue that indeed this holds modulo, these coefficients here diverge with Q and so on, but roughly it was working. But I was wondering for a while whether we can do it in two-dimensional CFTs and whether such a picture holds over there. So indeed, there is a very nice, and this is what I'm going to describe, there's a very nice setup that has been studied for a while before, where basically, let me write not to waste more time. Let me consider such a state, okay? So what I'm doing here is I'm taking this thermofield double at t equal to 0. I'm inserting on this left CFT some operator at some position x. I smear this operator in the Euclidean time with some small epsilon. This smearing is very important because if you don't smear this, the initial state, well, basically the energy of this initial state will be roughly delta, the dimension of the operator, over epsilon. Okay, so we want to start with an initial state that has finite energy. And then we perform a time evolution, which this actually corresponds to shooting some particle from the boundary into the bulk. Okay? These are actually very well tested setups by Tadashi and many collaborators after that, that describe so-called local operator quenches in two-dimensional conformal field theory. So this is like some milder version of a local quench, where we insert an operator, we break the translation invariance, and we do time evolution. Okay? And in this case, actually, we know a precise holographic dual for this one, for this case. So what the holographic dual is indeed the point particle. So we consider this point particle in the bulk, which has the dimension, which has a mass proportional to the dimension of the operator. And the point particle is such that at t equal to 0, this point particle is at this epsilon. So I'm using epsilon, but we could use some small parameter a here, which is really the cutoff of the operator. Okay, it's not necessarily the cutoff of the CFT. And as the t goes to, as t evolves, this point particle follows some radial trajectory z of t that falls into the bulk. Okay, so at least this part of the picture by Lenny, we have, at least for the states I'm considering, is very well established and has been tested extensively in many computations. Even we actually know how to take the bug effects from bug reaction of this particle on the background and so on and so forth. But before I go to the holographic computation, let me do the CFT computation of the spread complexity or Krylov complexity of this state. Okay, I explained to you that what the main object that we need to compute is basically the return amplitude, psi 0, where psi 0 is basically this normalized operator here. And it's a very simple exercise to show that this will be some thermal two-point functions of these operators computed on the left side with one position of one of the operator continued, well, written in terms of x and epsilon and the real time t. And basically, let me write this return amplitude for you. The return amplitude can be written as sine hyperbolic I beta t plus 2 I epsilon over sine pi epsilon over beta minus 2 delta. Okay, so this is all the return amplitude has the property when t is equal to 0, this is equal to 1, and then it decays with time for appropriate times later than this guy. Okay, and you can do the math of, or you can plug it into the code and check what the Lanczos coefficients are from, or you can compute the moments and test the Lanczos coefficients. And the Lanczos coefficients for this guy has the nice form. It goes 2 pi over beta n plus delta tangent 2 pi epsilon over beta, whereas bn's, they go pi over beta over sine 2 pi epsilon over beta times n plus 2 delta minus 1. Okay? So now you can stare a little bit at these Lanczos coefficients, and you still have the formulas written there on the board, and you can notice that, oh, but these are indeed the Lanczos coefficients that show up in the SL2R symmetry, modulo this alpha and gamma coefficients. You see that this gamma coefficient is 2 pi over this tangent here, and this alpha is just this coefficient, okay? So we know almost everything, and of course the dimension here, this h that appeared there, is this 2 delta. Okay, sorry, it's just delta in this case. So notice also here that you see this SL2R symmetry that emerges on the one-dimensional chain has the highest weight delta, whereas this SL2R symmetry in CFT actually has 2 copies of SL2R, which is H plus H bar, and so on. So they are not necessarily the same symmetry. Okay, this is one example where, even though you might expect it, that they are not the same. Okay, and then let's compute. So now we can use that formula with all the constants and so on. And where should I put it? In case, sorry. You mean in terms of your field? In terms of data. Yeah, there are L1 and minus, but only one copy on the chain, right? So I cannot see how they are written in terms of the original one. It's really just on dynamics on the 1D chain. Okay, but then we can compute this complexity, and it happens to have this nice form. It goes as beta square over 2 pi square. You get delta over epsilon, which is this E0 that I called before. This is basically the energy of this excitation. Then there's one more factor of epsilon, and there's sine hyperbolic square pi t over beta. Okay, this is what it is. And we can compute the rate of growth of this complexity, which can be written epsilon beta epsilon over 0 over 2 pi sine hyperbolic 2 pi t over beta. You can easily see how this happens and so on. Okay, good. So at least we have a prediction from the CFT side. This is the spread complexity, and this is the rate of its growth. And now we would like to compare it to this dual picture of a point particle in the bulk falling through this eternal black hole. Okay, so how do we do that? So actually, let's say we start with the left region. So we can write the metric r square over v square 1 minus mz square dt square plus dz square 1 minus mz square. Sorry, I suddenly switched to a to GR and ADS-CFT and so on, but I have not explained much why should it work. I noticed that there are many talks that explain things from the previous talks, so I still hope there will be a talk about ADS-CFT. Okay, and then this metric describes, so I studied two-dimensional, this is the computation in two-dimensional CFT. I consider a left region of this eternal black hole, or simply a BTZ black hole that has a horizon at z equals to 1 over square root of m, and then square root of beta over 2 pi is simply 1 over square root of m. Okay, that's the identification. And what we are interested, this is the prescription that Tadashi told us to do, is the bulk dual of this local quench state is considering some constant x, so some particle that starts at this position constant x, and then has a trajectory z of t. And we look at the Lagrangian of this point particle and the mass m. And the Lagrangian of this point particle will be, well, the Lagrangian is simply minus m ds, which will be minus mr 1 minus m z of t square minus z prime square 1 minus m z square. Fortunately, in our work on the local operator quenches, we actually solved that problem. And then we found this trajectory that starts at z equals to epsilon at t equal to 0. So at t equal to 0, we should be at epsilon, and then it falls into the bulk. And the solution is given by this. It's a little bit long, but so what we can see from this solution is that indeed at t equal to 0, this particle is, well, we can expand it. We can see that this particle is simply at epsilon. But one more thing we can see is that when t is roughly of order beta over 2 pi, which is 1 over square root of m, the particle, this term vanishes, and then the particle is in the near horizon region, okay? So the z of t is 1 over square root of m, and that's where you come close to the horizon. And actually, maybe interestingly, this was also noted here, that the rate of growth or the growth of complexity, if you look at this carefully, the time at which the complexity starts growing exponentially is also of order t over beta. Sorry, beta over 2 pi. So actually, this might be there's already some kind of one nice intuition that somehow when the complexity starts growing exponentially, this particle really goes towards the horizon of the black hole and then explores that region. That's where this growth of whatever. But then, good. So now, having this in our hand, we can compute the momentum. So how do we compute the momentum? Z of t. Well, this will be just a derivative of the Lagrangian with respect to z prime of t, evaluated on this solution. Okay. This will be just canonical momentum in this radial direction z of t. And well, you might have been like very excited about this, and then you know the explicit solution. Indeed, this particle falls into the bulk, and so on and so on. But once you do the computation, you get like quite a messy formula, and at the end you get that m over the momentum is given by m over epsilon and cosine hyperbolic square over pi t over beta, okay, plus something of order epsilon. So if you now look at the growth and then the radial momentum of this particle, something is not working, right? Like it seems like this grows for very late times, this grows too fast. It grows as exponent of, well, it could still be fine. It would still grow as an exponent of 2 pi over beta, but there's this cosine hyperbolic and sines, and something is really off. So you would feel like, oh, okay, maybe these ideas of Lenny were very intuitive, and maybe they were based on some other definition of complexity, and then maybe, you know, they actually in their computation they actually use only some kind of effective epidemic model. So okay, so yeah, late times they are maybe matching. So maybe this is fine, right? Well, but actually. Let me repeat this computation using different coordinates in the bulk, okay? I will first do the computation, and then I'll go to some comments about this, and then we'll see. So now let's consider coordinates. Yeah, the 5. We could have done it more general. Okay, and now in these coordinates, again, consider a particle. This coordinate rho is a proper distance from the black hole horizon. Maybe you're familiar with this metric. If you compute what's the proper distance measured from the horizon, it's exactly in this rho. Okay, and then again we want to have a particle that at rho equals to 0, it's at some particular cutoff rho lambda that we know how to relate to this cutoff epsilon. This is actually they are related by simply taking e to the minus rho lambda. And then once we solve it for such an initial condition, then we can compute again how that this point particle falls into the bulk from the boundary in this particular proper distance from the horizon. And the solution is again simple. You can simply change that solution into these coordinates and so on. Okay. And now, so basically, this is indeed the property at rho equals to 0. Exactly, you have a rho lambda, and then it goes towards the horizon as time progresses. Okay. And now let's compute this p rho, which will be derivative with respect to rho prime. This is of course easy to compute from this action. And once you plug everything and you plug this relation, what you're getting is that the momentum is simply beta over 2 pi mass over epsilon sine hyperbolic 2 pi t over beta. Okay? That's just a fact of life. So now you go back to this relation and you say like, oh, nice. so basically what you see is simply this factor epsilon or a that I was talking before times the p over rho. Okay? This is time like geodesic. It's a particle with mass m equals to delta. So here, of course, we also plug m equals to delta. And we see that indeed this radial momentum of this particle perfectly matches the growth of rate of complexity computed by the spread complexity of this state. Sorry? No, it goes from the boundary towards the horizon. No inter. Well, it's just from this perspective of this observer, it kind of goes and stays there, right, from the exterior observer. There are some, I have some comments on this one. Okay. I will comment on that. So first we thought like, okay, you know, maybe this is really, I mean, this is kind of interesting, but I mean, do we expect this or like what is actually happening? And then we repeated this computation. You don't need to take the black hole. You can just take, you know, these local quenches. We studied them for the vacuum or boundary CFT and you know, or CFT on the circle and so on. And we can do a similar computation, computing this operator growth. The spread complexity is analogous. Basically, this sine hyperbolic can be replaced by sine of pi t over L. Roughly, if you want to study the growth of the operator on the circle. And then again, you do the you do the same computation in global ADS, and then you see like if you do it in Poincaré or simple coordinates as you would expect, you get some messy formula that again something doesn't work, and again you realize that actually the coordinate you have to use, well, it's again the coordinate rho that you would expect. Okay, So if you use this coordinate for global, again, analog of this proper distance, then everything matches perfectly. You get the right momentum that matches, again, the rate of growth of complexity for pure ADS. Okay. So now maybe for the moment, how much? Yeah, I'm out of time. Okay. Okay, 5 minutes. So maybe the comment. So should we expect that or not? Like, it seems like we have some, so this relation, you know, I mean, one lesson from this is that, of course, Lenny is always right. You just, you just need to find the right computation for the claims. But so there seems to be a computation that reproduces these claims with the right prefactor and so on. But the point is that somehow from what we are learning is that, of course, you know, in CFT, we're doing some computation using very specific bases. And then, of course, you know, in general, we don't know the dictionary between, well, at least we would like to understand better the holographic dictionary to the precision that will tell us, like, okay, what happens if I change the basis on the CFT? What does it mean in the bulk and so on? Of course, we know that complexity measures should be somehow like this kind of measures, that they, you know, they will tell us something more about the isomorphism between bulk and the boundary. I don't know if this is really what's happening here, but it seems like, you know, we have some quantity in the boundary that requires us to use particular metric in the bulk to reproduce this claim. Yes. That's right. From the thermal, yes. No, not at least when I'm from outside the black hole horizon. If you, of course, now that there's an interesting issue, what happens when you bug react and what happens when you cross the horizon and so on. I expect there will be something non-universal there. But here, this result is just too much. I have noticed that I have not even taken the bug reaction from the point particle. So once I take the bug reaction, there has to be some more details and so on. I was just testing this proposal, you know, the bulk momentum and so on versus this complexity. So this is completely universal. And this is also for the times that the particle will not, you know, it's really for early times. Okay. But still, I think it's kind of curious that somehow this momentum, it precisely matches this, whereas in other coordinates seems to be off, but very like slightly off. At least the base in which we compute the growth of operators, it has a particular correspondence to the rho direction, where rho is the proper distance to the horizon. In ADS2, this metric is natural. That's what Lenny has been using also in his computation, so it's consistent with the SYK results. The initial state is, oh, I erased this. It was really this was the 2D CFT computation for this initial local operator quench state.
Was it A here?
A was the smearing of.
Is there, what is the reason 1 over A appears there?
What is the reason? Well, so the complexity is just this formula. And I'm computing independently derivative of complexity and the bulk momentum, radial momentum. I'm just saying they're related by this factor into DCFT.
See.
Which has to be finite because the energy of the initial state has to be finite.
Okay. Yeah, which
this is some sorry, yeah, this is some work that should appear soon with
okay.
with my postdoc and so.
So this is only up to the Zappadon time, right? So what happens later?
Yeah, good question. I think in 2D CFT, it's hard to do these computations for very late times. And also here in the bulk, this particle is really just like going to the horizon, and we see like semi-classical description and so on. I don't know. I think we can get a little bit more miling by studying carefully the bug reaction and so on. But even that, I think that will be early times. So I don't know. I'm maybe in SYK you can do these computations numerically for very late times, and there we know correlators for very late times. I think here it's just somehow universal. Yeah, you can think about it like this, that you can think about the C as being like some derivative of C as kind of probing this geodesic that describes the particle falling into the bulk. But in very particular coordinates.
Yes.
That's a bit funny. Yeah, late time independence. So other quenches. That's right. I mean, these quenches that are related, so finite size, finite temperature is the same relation between complexity and momentum, and the same choice of the bulk coordinates. I would like to understand it more non-trivially, like in, I don't know, some less universal cases and so on. For the moment, I just wanted to establish a little bit, like, you know, whether something like that can hold and in which cases and so on, because now we really can do a CFT computation. Whether it's universal or not, that's a second question. It's really a CFT computation of a certain complexity that matches this. We have not done much of this. Okay, so there might be some better ways of like maybe there is still a way of making it more covariant. So you could maybe, you know, like you could maybe dot this guy with some vector, blah, blah, blah. And then this vector you have to define somehow in the bulk. In the literature, actually, people studied something similar where they said that, okay, we have to first compute some maximal volume in the bulk, then find the slice, the maximal volume slice in the bulk, find some vector that is perpendicular to this and dot the momentum to that. Maybe this should be the proposal for the correspondence, but I don't see how should I add this maximal volume momentum to the story and so on. Like there could be, I don't know. Like I think this maybe there is indeed some property of the metric in which the square becomes just simply that.
Yesterday you were telling about some Krylov metric. Is there some related to Krylov?
I don't know. Yeah, good question. So unfortunately, I did not have time to talk about the second part, but I will refer you. This was probably something that Julian would talk about, which is the application of this spread complexity to the SYK model and the double scale SYK model, where you can see that there the Krylov basis also is very natural, and that Krylov basis is basically a chord diagram basis, and in the triple scaling limit that becomes a length basis in the bulk of JT. So this Krylov paradigm is very natural and kind of nice in that story, and now at least we have in some regime we can also establish that Krylov complexity there is related to some regulated length in JT gravity. I refer you to Julian's papers. Thank you.